Okay, hi folks. This video segment is for chapter 13 of my book. So let me move on to the slideshow here. So the book is Finite Element Essentials in 3D Experience, release or revision 2021x. And the particular problem chapter I'm going to be doing is chapter 13, which deals with linear buckling analysis. The problem that we look at is uh, a frame like that, okay, which has obviously the dimension and there's a thickness here, so the square cross section. And this is under a buckling, under compressive load, like so. That being the case, you can see that there are two planes of symmetry here. In fact, if I assume that there is no out of plane buckling, there is three planes of symmetry, okay? So what I'm going to do is I will actually make the entire model, and then I can either make it part like that, or I can make the entire model and start cutting it with different planes. Maybe it's better if I did it like so. Actually created the model in that way, because I know at the end of the day, this is what I have, okay? And standard properties of steel, and we move on. Okay, so let me go ahead here, and I'm going to start with the part file. Okay, it's right there. And on a convenient plane, on that vertical plane, I will sketch what you saw in there. So it looked like so, it looks something like this. I'm going to clean it up in a minute, but for now, let me make the general shape. Okay, so let me see now. These were units of inches, okay? Just to remind you how we change into inches. So we're going to go into uh, my photo here on the right-hand side, preferences, and under units, you can take the length, which was millimeter. I guess I have to expand this box, so we're going to change it to inches, okay? And the force from Newton, we're going to change it to lbf. Now, because I'm specifying the Young's modulus, so that will be stress. I'm just showing you how to do all of them. You can sort it out in the alphabetical listing by clicking on magnitude. This becomes alphabetical. Maybe easier to find it out like that. Let's see, where is the stress here? We have a stress somewhere. Okay, where is it? S. Okay, first of all, pressure. Okay, where is the stress? Let's see. Stress, right there. I'm going to change this thing to PSI. Okay, good. So we say okay, we get out of here. Let's start putting dimensions here. So the dimensions for this was 10 inches, 10, and for this is also 10 inches. Fit it, standard or sketch. Let me see. Where is the fit here? Sketch. Maybe forget the tools. That's kind of weird because the fit must be somewhere there. Be on that side. It's weird, very strange. Oh, there. Okay. View, fit. Does it fit? Yeah. Good, good. So let's put the rest of the dimensions here under dimension. This is 1 inches, and this is 1 inches. All right, good. So we exit and we pad it. I'm going to pad it by half an inch because in principle it was 1 inch thick, but then we made a cut through it, 0.5. Okay. All right, so this is my geometry that you see there. All right. Now, we have to apply material properties, and we're going to do it like that. Tools, create a material. I'm going to give it the name chapter 13. I should have called it steel and didn't keep using it, but that's not how I'm doing it. Okay, so there is a chapter 13 here, right there. If I right click on it and say simulation, I can put my numbers right here, okay, and then apply it. Or I can apply it on the part, and then there's going to be an empty shell there, so I have to fill in the data over there. So in the book, most of the chapters I do it like that, but here is I'm going to say simulation, abacus multiphysics, mechanical, elasticity, elastic, and I put those numbers here. It was for steel is 30, Young's modulus is 30 megapascal, 30 million psi, so 30 e to the 6 psi, and Poisson ratio is 0.3, and we say okay. Now we're going to say right click apply, and I'm going to close that. I don't need it anymore. I put it on the part or on the tree and a check mark. In fact, the material properties has been created there, and the data, instead of me putting it in this position, is already inputted from the previous step. You can see that. Okay. All right. So this is all done, and we're going to go to uh, structure model creation. Now, the software immediately sees a solid object, so it meshes it automatically by itself without me telling it. It's right there. See that? You can do that. Now, of course, you can change the size of these things, etc. So I will keep it like this. I'll keep it like that. Okay? And it uses the proper material properties put in the solid section. No problem. Right there. Now, uh, uh, okay, so we are done. This is your structure model. So now we're going to go to scenario. Scenario. It's a structural problem. Immediately you get the thing at the bottom, 2 exclamation marks, because I don't have a finite element model. I have not picked it, and I don't have a step. Okay, so when you go to setup, this is what allows you to pick the finite element model. You click on it and notice that there's only one here that I've created. So I select it and you say okay, and immediately this turns green. Okay, notice that the second exclamation mark here on the right is still red. That's because we don't have a procedure. So we go to procedure, and we want to do a buckling analysis. There is your buckling step. Okay, you click on it. Ordinarily, it extracts 10 modes of buckling, the first 10 critical values, but of course the first one is the most important one, so we say fine. All right, so we need to specify the restraints. So the restraints are, you click on the restraints, and first of all, there is 3 planes of symmetry, namely the one over here at this end, the bottom end, and the back or the front. These are planes of symmetry because we made symmetrical cuts. So we have to do this thing 3 separate times. You can't do it all at the same time. So you select this and the front face, for example, or the back face. It really doesn't matter, but just make sure you know which one we pick. So if we pick the front face, this face, as plane of symmetry, then the load that we're going to apply is going to be at the corner point which is closest to us, which is fine. So we select this. Notice that you cannot do multiple selection. We say OK. And then another one, which is right here. Say OK. And another one, which is down below. That's a plane of symmetry. Now, because the background is pure white, you can't see really well where these icons are. So let me change the background, ambience, dark mirror. Okay, there we are. So now you can see that there's a plane of symmetry here. Get closer, you can see that plane of symmetry here. There is one on the front face, it's right there, and there is also one at the bottom face, which is kind of hard to see, right there. Okay. All right. So let's go ahead and keep it like this, or let me change it back to the same color that we had before, pure white. Okay, very good. Actually, the one that I had was white mirror, something to that effect. Okay, now we're gonna apply the load. The load. So we're gonna apply a concentrated force at this corner point right there. So when I select this corner point, notice immediately it sets up a coordinate system for me, and I want to apply that load so that it's at 45 degrees with respect to the y-axis. So one way of doing it to model it exactly like what I had in the transparency is to rotate this coordinate system by 45 degrees about the x-axis. So what I can do is that I can put 45 here, oops, 45, and hit return or enter. Notice that now we can apply a load in the z direction. So here, load in the z direction, I apply 1 unit, but it has to be -1, of course, if you're compressing it. -1 unit, LBF. Okay, there we are. Okay. So this is going to be our dummy buckling load, and then we're going to run the buckling analysis, and whatever multiplier we get, we multiply it by 1, and that's going to give us the critical load. Okay, so we got everything. Restraints we did, load we did, and now we're going to go to simulate. First, let's make some checks here, model and scenario checks. Worked fine. Then we're going to do simulation checks. Any error messages, warning messages that may be involved in this problem are going to pop up in these stages. It's a good idea to do these. But if you're 100% sure that it's going to work, then just go ahead and do the simulation, which is the last item right there. Okay. Okay. Good. So this is done. You can check the warning method to see what it was. This is fine. It says that I'm really not sure what this message says. Okay, let's go and simulate it. All right, so let's run it. Now this problem. It was probably more appropriate to be done with beam elements, but we decided to use solid elements, so just be aware of that. You can always do this hand calculation for this problem using frame analysis and beam elements and things like that, and uh, use it as a reference to check it against the calculations in 3D Experience. All right, we got it. So let me close this. So this is the first load. This is the first load. Okay, first buckling load is this number multiplied by 1 unit that I applied, 1 pound force. So it's going to be 42,000, whatever. And then of course these are the other ones. Some of these may not make sense physically, but this one definitely does. We know that it's the buckling mode is going to look like that. And so as you go further down, these become more meaningless. Okay. The first critical point, of course, if it buckles, then it's going to, majority of cases, if something buckles, you're considering it failed because it's going to it's going to move further and further, translate further and further from the initial configuration. Stresses are going to go up, material will eat, etc. So anyway, these things are all meaningless. These are all. This one is okay. This one is okay, but it's going to be very difficult to create this buckling mode. The one that usually happens is this, and then pretty much after that, it's going to, in many cases, it's going to collapse. Okay, for beams and frames and things like that. Okay. Yeah, that's pretty much it. You can also plot the displacement, which is really meaningless. Okay, and that's it. I mean, obviously stresses are totally useless. All right, folks. So good luck. We did this problem, and you're on your own. Oh, yeah, there's something that I forgot to tell you, and that is actually the buckling load is going to be double of this because we modeled only half of this structure. Remember, we cut it into half. So you really have to multiply this thing by 2. So the 1 pound dummy force times this eigenvalue times 2 is going to give you the actual compressive buckling load that you're going to apply there.